Our project is a comparison of QR and SS inventory policy under some uncertainty. In the problem statement, we are considering the lead time is not deterministic. We are considering it as geometric random variable. We make the following assumptions. 1. The system is continuous review. 2. Demand is random and stationary. And order probability is constant throughout the time period. In this scenario, we have applied SS and QR policy and compared the performance of both policy by simulating and optimizing. In the abstract part, we use the net profit as the object function for optimization experiment. We compare the differences in profit for both policies due to this effect for two different values of order probability. We repeat the experiment for a higher value of item cost. Finally, we design a factorial experiment to quantify effects of item cost and order probability on the net profit. Now the cure policy. The cure policy is place an order of order quantity Q when the inventory level is less than or equal to the reorder level R. The SS policy. When level of on-hand inventory is less than or equal to small s, an order for the difference between the inventory and capital is placed.
So this is the model which we have used for our simulation project. These are the parameters which are used. For our objective function, we are considering the profit earned over the whole time period. We have also kept track of other important variables like stock, opportunity loss, overstocking loss, number of orders, etc. For our sales, we consider the sales are recorded at the end of each day according to the demand parameters. Now let's have a closer look at the retailer agent. So the retailer agent moves between three states. When the stock level falls below the reorder level, it moves from the state stock to understocked and it tries to place an order. According to the geometric random variable, once the order is placed, it moves into the order state, and then after a deterministic lead time, it moves back into the stock state. Let's have a look at the order agent. So we have modeled this as a separate agent because we are considering it to be perishable and a finite expiry date. So once the expiry time is complete, it cannot be sold anymore, and it goes into the overstocking loss.
In this model, we have taken the parameters to be these, and the lead time is 5 plus y, where 5 is the deterministic part and y is the random variable following geometric distribution with parameter p. So we have conducted factorial design experiment with profit as response and item cost order probability as the two factors. For both the models, we find that the main effect of item cost and order probability have been found to be significant, whereas the interaction effect of the factors were not. So to see how or whether the mean profit is significantly different for the two policies, we have done paired t-test. From the given table, we find that for the first three cases, the mean profit was significantly different, whereas for the last one it wasn't. Then to check which policy performed better, we have the second table from where we can see for the first and third case, QR policy performed better than SS policy in terms of profit. In the second one, SS policy performed better, and for the last one, there wasn't much difference.
So here we recorded all our possible combinations of parameter values, and this is the summary. So this is the graph where we are comparing the mean profit for both policies, and it has been analyzed already in the t-test. And this is the regression equation which is based on the factorial design experiment what we did earlier. So coming to conclusions, QR model does not perform more statistically than SS model for all but of the tested configurations, and for item cost 40, SS policy gives a higher profit than QR policy, but for item cost 20, QR policy gives much higher profits. Thus we can conclude that as item cost increases, profitability of SS policy also increases, and the increasing performances of QR policy with decrease in the order probability can be attributed to the fact that overstocking is less likely in QR model as observed. And possible extensions and suggestions, we can investigate a scenario where the retailer can update his policy parameters based on lead times observed in last few time periods to better fit the situation, and we can model varying order probability over the time period. and these are our references, and thank you.